So now let's say you also start to play poker with your friend Rob. Rob's set of facial expressions is a bit more sophisticated than Sam's. Not only does his mouth angle move, his face also changes color intensity. Given the success of your single neuron model in predicting Sam's bluffing, you decide to give it a go with Rob. But given Rob's much greater variety of facial expressions, you can't just consider mouth angle. You have to also consider face color intensity. You program your trusty smartphone so that it can capture not only mouth angle, but also facial color intensity. You use the same perceptron model that you used before, but now you have two-dimensional data that will contain features of both mouth angle and face color. You play rounds of poker with Rob, once again collecting data and recording both the angle of his mouth, the color intensity of his face, and whether or not he was bluffing. After many rounds of play, you've got your data, which is Rob's mouth angle, his face color, and whether or not he was bluffing for, let's say, 100 rounds of play. Because we still only have two dimensions, we're still able to visualize what this looks like. So let's see what it looks like on a graph. It seems like there's a pattern to when Rob is bluffing, because he basically seems to be bluffing when his face color gets paler and when he's tending to smile. Notice that unlike the one-dimensional example, it's not a single face color intensity value or a single mouth angle at which the truth becomes a bluff. Instead, it's some combination of the two where this transition from truth to bluff occurs. To be more numerically precise about this, you use your newly collected data to train your perceptron model. Let's remind ourselves again, the perceptron model needs to find a weight value for each dimension of the input. So now we have two-dimensional input, which is x1 for mouth angle and x2 for face color. The perceptron needs to find two values of W, W1 and W2. The W1 is going to be the weight for the mouth angle input. W2 is going to be the weight for the face color intensity. There's also the unique bias value that the perceptron needs to find. The model finds that the first weight, W1, should be 0.8, and then the second weight, W2, should be negative 1.3. This means that when receiving the inputs, the model should weight the value of the mouth angle by 0.8 and weight the value of the face color with negative 1.3 and then sum them together. There's also the unique bias value that the perceptron needs to find, and here the perceptron learned the bias should be 4. So the sum is going to be the weighted inputs plus the bias, and then that's going to be fed through the activation function to produce an output. Once again, we're going to use the step activation function, which means that if the sum is less than 0, the model is going to output a 0, and if the sum is greater than or equal to 0, the model is going to output a 1. So let's see how the model makes predictions for different values of mouth angle and face intensity. So if the mouth angle is 8 and the face intensity is 5, the sum is going to be 0.8 times 8, the mouth angle, minus 1.3 times 5, the face intensity, plus 4, which is the bias, and that equals 4.9. And 4.9 is greater than 0, so that means the activation function will have you output a 1, and that's a bluff. Now let's say Rob's mouth angle is 4 and his face color is 7. Well, we feed this into the sum, and then we've got 0.8 times 4 minus 1.3 times 7. We need to add the bias, which is plus 4, and that comes out to negative 1.9. So negative 1.9 is less than 0, so that means feeding through the activation function, we get a 0 as an output, and that means Rob is telling the truth. So Rob is telling the truth when his mouth angle is 4 and his face color intensity is 7. Let's do it again. So we've got mouth angle of 0 and then face color intensity of 6. So that then the sum would be 0.8 times 0 minus 1.3 times 6 plus the bias, which is 4. And that equals negative 3.8. Negative 3.8 is less than 0. Feeding this to the activation function, we get a 0, That means Rob is telling the truth. One more time. If we have a mouth angle of 0 again, and now we have a face color intensity of 2, we do 0.8 times 0 minus 1.3 times 2 plus the bias 4, and that equals 1.4. 1.4 is greater than 0, and so the activation function output is going to be a 1, and that's going to give us a bluff. So you can see that the predictions of the model reflect what we see in the data, which is that when Rob is more smiley and when his face is more pale, he tends to be bluffing. Now remember that the calculation for the 1D perceptron model was effectively a straight line followed by an activation function. The calculation for a 2D perceptron is doing a very similar thing to the 1D model, except for instead of an equation for a straight line, the sum now is an equation for a plane in 3D space. So I want to show you the visualization of the 2D perceptron model. So we've got the input data, which is mouth angle on the horizontal axis, and we're calling that x1. And then we've got face color intensity on the vertical axis, and we're calling that x2. So instead of the line that we had for the one-dimensional perceptron, the sum is now equivalent to this plane that cuts through this two-dimensional plot. To visualize this, I'm going to flip this graph of mouth versus facial color around and turn it on its side. So now we have the two-dimensional plot lying flat, and the sum is going to be represented with this axis that is coming out of the page. So then we have a two-dimensional plane, and this two-dimensional plane is the visual representation of the sum. And remember that sum was 0.8 times x1, which is the mouth angle, minus 1.3 times x2, which was the face color, plus 4, which was the bias. Here you can see the dotted red line is where the plane intersects the graph. This dotted red line is all the points on the graph where the sum is equal to 0. Because remember, this axis coming out of the plane is equal to the sum. So this line, this red line of intersection, represents the data points where the mouth angle and face color values are such that the sum is changing from negative to positive, and thus representing the points where the model's predictions are transitioning from being truth-telling to bluffing. Finally, we need to feed our sum through the activation function, which makes the negative value 0 and the positive values 1, and we can see the activation function being overlaid in 3D on top like this.